Welcome to the seminar of the Astani Department of Civil and Environmental Engineering. This might be one of the last seminars of the year as we get close to commencement day. So today we are honored to have Sharon Walker to give us a seminar. Professor Sharon Walker, she is actually the John Babbage Chair in Environmental Engineering at the University of California, Riverside. And Sharon is one of ours. She graduated from USC with actually 2 degrees, one in environmental engineering and one from the college in environmental studies. And then,
the Dornsife College.
The Dornsife College.
Oh, it's been named.
It has been named. No longer LAS now. We can call it the Dornsife College of Letters, Arts, and David.
Dana and David.
And Dana, okay, let me start again. Okay, so she
At least they're easy
graduated
names
from
to
the
remember.
Dana and David Dornsife College of Letters, Art and Science. I thought that to say Sony Astani Department of Civil and Environmental Engineering was hard to say. Things don't move to the college. Anyway, we are very honored to have Sharon. She graduated from Yale University and got both MS and her PhD. And then she joined UC Riverside, where now she's an associate professor. Along the way, she has collected all kinds of awards. I will not read all the awards here. We have to proceed with the seminar. But she has quite a long list of awards. And if I can jump, I should say that she has been awarded in 2010 the NSF Career Award, which is a very prestigious award. She was also a Fulbright Scholar at Ben Gurion University in Israel, and that was in 2009, 2010. So we are very honored to have Sharon. Sharon, welcome.
Thank you. I appreciate the applause. May I deserve it? It's really lovely to be back. Thank you for the invitation to come speak to all today, both here in the room and wherever you may be, sitting at your desks watching this as well. So thank you for coming. I know this has been a long series of seminars, and the school year is almost over, and I'm flattered, especially the students who had the energy and are here. Thank you. So today I'll talk about work I'm doing as part of the University of California's Center for the Environmental Implications of Nanotechnology. This is a major center that's based out at UCLA, and UC Riverside, UC Santa Barbara, UC Davis are the primary partners, along with many others across the world. And this is a center that's aimed at, it's a preemptive effort funded by the NSF and the EPA to identify the hazards posed by nanomaterials getting into our environment and identifying the toxic components and the risks that are involved so that we can design smart particles that will not be problematic or cause the next environmental disaster. So really trying to think ahead of where technology is going and to avoid any kind of risks. My particular piece of this puzzle is looking at the fate and transport of nanomaterials that have been released into aquatic environments. And I'll be presenting those elements today. All right, so nanomaterials have effectively worked their way into everything we use. Many products we don't realize that they're part of, and in the production of them, there's lots of wastewater, lots of aerosolized waste, and as well as dry waste that come from this process and can potentially lead to the release of these materials into our environment. So there are many products that nanomaterials have really improved, right? We like buying the athletic gear or the shoe pads that are anti-fouling or anti-fragrant, right? Because they're antibacterial properties. We all like our ultra-light composite materials that are in sporting equipment and our all sorts of various things. We all like our little iPods and little phones, right? So nanomaterials have made their way into our lives and they're here to stay. And of course, the reason why they've made their way into all the products we use in so many different areas is due to their extraordinarily small size, which renders them with a very high surface area and very specific, wonderful chemical properties that allow them to be very reactive, have distinct optical properties, chemical properties, and the like, that only come when they are in nano form, not necessarily the micro form. And they can come in a variety of different forms: dry powder suspended in gas, nano-aerosols, which Kostas knows quite a bit about. But also these materials can get into water in a nanohydrosol and can be very reactive. And also they can be embedded in some sort of composite. And in these various forms, they have a really wonderful wide range of applications. In medicine, we're using them for the new types of imaging. They're used for drug delivery, in energy. There's considerable amount of research developing new solar panels and solar cells, fuel cells that require nanoparticles in them, electronics, of course. We all like the super small, whatever it is, our phones, our iPods, and the like. And nanomaterials have made it into a variety of our consumer products people don't realize: our toothpastes, our sunscreens, and the like. Now, today I'll be talking about nanomaterials in a negative way, but I do want to say that from an environmental perspective, not all nanomaterials are bad. Because of this extraordinarily high level of reactivity, they make a wonderful remediation tool, and there's a lot of different strategies that can utilize nanomaterials that are very worthwhile. The challenge we run into is that when these nanomaterials are in water, we're seeing them interacting with different organisms and causing toxic response. There's a growing body of literature that shows that nanomaterials can lead to toxicity. So carbon nanotubes, zinc oxide, titanium dioxide are examples that are cytotoxic to bacteria, mice and rats. Fullerene buckyballs, which are extraordinarily widely used, are toxic to both fish and humans, and various metal nanomaterials like quantum dots and silver, nanosilver, are toxic because you can actually have leaching of the metal ions, and those can actually lead to a toxic response and kill cells. The actual mechanism of this toxicity is something that's widely debated in the literature right now. But we're seeing evidence, and this clearly suggests that if these materials are getting into our aquatic systems, and our algae and bacteria and fish and other sorts of organisms, and ultimately us, are exposed to them, it definitely suggests that we need to be concerned and be preemptive about this. One of the challenges we run into is the fact that we are exposed to nanomaterials, or have the potential for it, at multiple stages of the life cycle of various products. We can have nanomaterial release during the raw material production or during consumer product manufacturing. So there can be a slurry of waste from making a solar cell, for example, that might have different nanomaterials in them, and those can get into our wastewaters. They can also be aerosolized. I admit my bias is towards considering them once they're in the water. They can also get into the water during consumer use. A perfect example are the various face creams, cosmetics, for example, that have nanomaterials in them. And when we wash our face, they're instantly being put into our wastewater system. And one of the big concerns is what to do with them at their end of life. How do we store them successfully? Are landfill liners sufficient to retain them, or is incineration going to release them? All of these are potential exposure routes and ones to be concerned with and keep an eye on. Some examples of nanomaterials. These are very commonly used ones. You can imagine with these pictures. We've got some titanium dioxide here, quantum dot. Carbon nanotubes come, of course, in single or multi-walled forms of the graphene, and of course the fullerene buckyball, the C60. My work has been to date primarily with metal oxides, and today I'll be talking virtually extensively on titanium dioxide. And these are some images we took in my lab of our titanium particles. These are for those of you who are interested in anatase form, and their primary particle size is averaged about 18 nanometers. So they start out quite small, although you can see aggregation is an issue. Now I chose to work with titanium because of how broadly used they are, and they're in our sunscreens, as I mentioned, our toothpastes. They're used in paints because of very reflective properties, and it's a marvelous catalyst. It's actually used in disinfection processes. And titanium is actually extraordinarily useful for a lot of environmental applications. It's very extensively used. In fact, the U.S. is the largest producer in the world, and we're producing 4 million metric tons per year of just nanophase titanium dioxide. But as I mentioned, these have been found to be toxic. And what's important here is not just to prokaryotic cells. Some people say, oh, it's just toxic to bacteria. But we're actually seeing toxicity to eukaryotic cells, which is a concern to our health as well. What's really a bit staggering at this point is we're actually seeing measurable levels in wastewater and biosolids that are concentrating the nanomaterials that are getting into our water and getting detectable. One of the challenges up to now is that I think the analytical chemistry world hasn't caught up for the detection for nanomaterials in water because it's so dilute. But where we see this sort of concentration effect in our wastewater streams, these levels are measurable and at the levels that have been seen to be toxic. So it's a concern. And this is only going to become more of a concern as our use of titanium dioxide in this nanophase grows. So this is a figure out of a paper that came out in the Environmental Science and Technology going on now a couple of years ago, where they looked at the relative use of nanophase versus non-nanophase titanium dioxide. It's a little hard to see, so I'll just point out, over the last few years, we're just about here, titanium is a minor fraction of the total titanium production. But from this actually quite rigorous study, prediction is that it's going to surpass the use of bulk phase titanium and really become extraordinarily high in production. If we're already seeing titanium dioxide in our wastewater at these low levels of production, we should be concerned what's going to happen when the production over the next 20 years just goes up exponentially. What happens to these particles once they make it into an aquatic environment? They can go through a range of these. This is sort of an idealized system. They can be suspended. They can actually stay mobile and move with advective forces, and in some cases stay dispersed depending upon the chemistry of the particles. They can aggregate, and if appropriate, depending upon the density of the aggregate and the density of the particle itself, they can settle out, and with certain mixing properties can be resuspended. Additionally, one other mechanism I've added to this slide is that they can also, once they get to the sediment layer, be transported into the porous media and make it into the sediment below. And these are the three areas that I'm particularly interested in, looking at the aggregation, settling, and transport of these materials once they're introduced into the water environment. So a little bit about my particular lab's focus. We're really interested in a fundamental study of mechanisms involved in the movement of these particles. How stable are they? Are they aggregating? Are they being removed by any of these processes I mentioned? In either the natural or engineered environment. So when I'm interested in porous media, it could be a filter in a local water treatment plant, or it could be in the subsurface in soils. So today I'm going to go through three sub-projects that we've been working on in this area. The first is actually in the development of some handling protocols and working with nanomaterials, looking at the effect of how we prepare them for even conducting a fundamental consistent study. Then I'll get into the real meat of the talk, which is looking at the role of particle concentration, solution chemistry, and hydrodynamics on the fate of these nanomaterials, specifically titanium dioxide. And finally, I'll share a bit on what we're doing with how natural organic matter and bacteria contribute to the transport of these nanomaterials. All right. The way in which I approach this is admittedly idealized, right? We wouldn't be engineers if we didn't start thinking of everything as a sphere. But if you can imagine a collector grain in a packed bed or in the subsurface momentarily, and as particles move in water around that grain, they have the opportunity to interact with that surface and be removed. Now, when we're in a three-dimensional packed system, there's all sorts of additional mechanisms of removal that come from that three-dimensional pore structure. And we can capture this in traditional packed bed columns. And so I work with a range of actually saturated and unsaturated systems to quantify. You can actually use this to quantify deposition rate coefficients to identify the removal. So actually this is a very nice quantitative way to calculate the removal of these particles in the pore structure. And I use two other systems which I'll introduce together. The first is the radial stagnation point flow system, which allows us to look at the particle interactions with a surface when flow is perpendicular, as the particles first approach a collector, and similarly when we can use the parallel plate flow system to identify how many particles are removed when flow is parallel to the surface, so where the shear forces are more pronounced. So we can use either of these flow cells and these geometries to visualize nanoparticle removal. And it's actually very exciting because we've developed a technique of fluorescently labeling the particles so that we can actually see the nanomaterials, see them aggregating, see them attaching to the surface, and disaggregating and detaching from the surface. So it's also with these two methods on the right, these two systems, we can calculate mass transfer rate coefficients. So we visualize the particles. Hopefully this shows up a bit for you. These are actually titanium dioxide particles. We worked at a system where we had the minimal aggregation. So these are, in some cases, primary particles. We can count them one by one and plot the number of particles depositing as a function of time. From that, get our transfer rate coefficient. And this is the value that we can compare in a pretty rigorous way between these various conditions. So this first project is developing a protocol. The reason why this is important is the literature is really, especially those of you who are students can appreciate it. You go and read the method section of papers, and you see everybody has sort of their way of handling the particles, right? They buy it and it comes dry. Well, what do you do with them? Somebody might put them in water and sonicate overnight, and somebody else might put it in some sort of other solvent and and sonicate for 30 minutes. And then they go do the same experiment, and then they try to compare them. And those are apples and oranges. We can't compare those. So as part of the center I'm in, I was asked to develop a protocol that could be consistent and get reproducible nanoparticle state so that these subsequent transport and toxicity tests would really have a consistent nanomaterial to compare. So start out looking at first dry particles that we would order from a manufacturer or obtain from a material scientist and the team that had synthesized them. We would put them in water, and we did a first analysis of the sonication effect, then the contribution of ionic strength that we were testing, and then on the concentration of the nanomaterials. And this work was published last year in Journal of Colloids and Surfaces A, which is the physical chemical focused journal. All right, and then we did a series of characterizations. We did size analysis with dynamic light scattering. We did electrophoretic mobility. Additionally, some looking at some images with SEM, although I'm not getting into some of that today. So this is just a flow chart we put together. We worked in this case with titanium dioxide, cerium oxide, and zinc oxide, where we worked with a range of concentration of the nanomaterials and put them in a salt solution and sonicated them anywhere from 0 to 60 minutes. So it was really very well controlled. And tried to find the optimum condition where you could sonicate it and have the smallest possible particle, where you break up the aggregates. And we found that we could have consistently the lowest hydrodynamic diameter at a 30-minute sonication. So this became our time that we continued to utilize. And that made our nanoparticle stock solution from which all other experiments were done. Then we wanted to identify, well, how long do you need to sonicate it once you now resuspend it? Because you now have this aqueous solution of nanomaterials and you want to do something with it. You want to add it into another solution. You want to do some other study. How is that other condition going to affect them? Especially if you want to now test it in a different solution chemistry. So we did a series of tests where we diluted the nanoparticles further and looked at sonication to identify, again, where we could have the lowest diameter and found 30 seconds was the best for really consistent size distribution, and subsequent particle characterization. And so this is the protocol that this UC center is utilizing. Some examples of the ionic strength effect. This is electrophoretic mobility as a function of potassium chloride concentration on the x-axis, and to the right is the effective diameter measured by dynamic light scattering. So just some important trends, and I'm sorry, for some reason, this should be red.
It is actually.
Oh, it is, okay, so it's just the
I think
projector.
we've got a problem with our cable here.
Okay, well, good, so you can take a look at that. Well, we can go by the triangles, right? So we can see that for all three of the metal oxides we worked with, there was a sensitivity to salt concentration. They were positively charged. This was at an unadjusted pH. They were positively charged in solution and became slightly less charged at higher ionic strengths. And that corresponded to less charge, less repulsion, more aggregation, and with that aggregation we saw an increase in the effective diameter. So the particles you work with are very much a function of the salt solution you're going to put them into. Also, the amount of particles you utilize in your study. So this is another thing when you're reading a paper and you see, well, this study used 1 milligram per liter, and that study used 100, and that study used 600 milligrams per liter. How does this affect our results? Well, it can do an enormous amount. It can actually change the pH. We saw, particularly in the case of zinc oxide, a substantial increase in the pH when we increased the number of particles. Similarly, with zinc oxide, we had dissociation of the metal ion, And so we saw an increase in the conductivity as well. And so these systems are very, very sensitive to the concentration. Interestingly, we see that, and again, these are the triangles that are red on some of the screens. The electrophoretic mobility, or the charge, remained quite constant for the ceria across these concentrations, but for the titanium, there was an increasing trend. And well, the zinc was all over the place, but we understand why, because it's got this dissociation occurring. I just bring this up and want to emphasize it because when you are studying the nanoparticles, you need to ensure that there's consistency. So one cannot do a study in one concentration and directly link it to the phenomena observed at a study conducted at another concentration, because you will have entirely different, not only particles and aggregate sizes, but also solution chemistry. All right, so moving on to the work that we've been doing in both the column that I spoke about and the parallel plate system, looking at the role of nanoparticle concentration, solution chemistry, and hydrodynamics. And this is work entirely done with the titanium dioxide. So our columns were very short. For those people who study columns, ours are about as short as they get. They're about 5 centimeters long, working with ultra-pure quartz, highly clean quartz. And we worked with 2 ionic strength conditions and 2 pHs and 2 flow rates so that we could look at solution chemistry effects and flow rate influences. These 2 pHs were chosen because the isoelectric point of titanium dioxide is 6.2. So at pH 5, we've got a positively charged particle, pH 7, a negatively charged particle. And at both conditions, the quarks themselves are also negative. So from the point of view of thinking about repulsive conditions, at pH 5 it should be quite favorable. Positively charged particle, negatively charged quarks. One would anticipate electrostatic attraction, whereas at pH 7 both particle and surfaces are negatively charged and should be quite repulsive. So here's some examples of our breakthrough curves. On the y-axis is the relative concentration breaking through the column. As a function of pore volume, you can think of this as time as the particles break through the column at the 2 velocities. Just to start off, at pH 7, what's important to note is that, again, I'm sorry it doesn't show up here, but pH 7 is the blue and red for those of you who can see in color. pH 7, now this is the condition where there were negatively charged particles, negatively charged quarks. We expect repulsion, we expected tons of particle breakthrough, and yet virtually it was complete removal. So from the point of view of we want to remove nanoparticles, this was an exciting moment. But we saw no removal, or excuse me, no breakthrough under either flow rate. What was surprising and a little bit perplexing at first was that at the low velocity, we saw breakthrough at conditions that we expected to be favorable. We expected the maximum amount of retention under these chemical conditions, and yet we saw breakthrough at either of the concentrations, 100 or 200 milligrams per liter of particles in solution. Similarly, at 10 milliliters per minute, we saw a breakthrough also at those conditions, and one additional one, which was the higher ionic strength. So we see now here an effective ionic strength, an effective pH, and also a notable effect of the velocity, because the magnitude of what was eluting from the column was much higher at the higher velocities. So there's a range of possible mechanisms, and I'll walk through each of these and hopefully convince you that it's a combination of them. So the first thing we did was to cut up those columns after the experiments and dissect them and look at the retention of the nanoparticles as a function of depth through these columns. And so you can think of this as the top of the column working its way down to the outlet of the column. And the y-axis is the concentration of particles retained as a function of what was injected per mass of the quartz. So effectively, how much is retained, this being the highest amount and lowest. And note that this is on a log plot here for the 2 velocities. Now the systems where we saw particles being eluted, we saw some interesting trends. This was the one at the lower velocity. The amount retained at the top was not as high. It was retained at the top some, but it was consistently high level of retention through the entire length of the column. And it was the same thing at the higher velocity, a consistently high level of retention through the length of the column. Whereas the systems or the conditions where we expected entire transport, entire breakthrough, we actually saw all the retention was at the top. The particles were basically being removed. There's clearly some sort of physical-chemical retention mechanisms, likely straining, retaining them at the top because the concentration dropped off to virtually nothing over the course of the length of the column. And as I mentioned before, we really anticipated something very different due to the interaction energy. So DLVO theory combines the interaction forces from electrostatic double layer and van der Waals forces. It's a good way to get a first approximation of how much interaction you will have between these surfaces. And so in the positive range, it's repulsive. In this range, it's attractive. So at pH 5, where we saw breakthrough, we expected it to be attractive. So again, why was this the case? And when we saw the repulsive conditions, we saw retention. And so this would suggest that that retention has to have some sort of other mechanism. I just want to point out we made these calculations as a function of particle size. Or you need to have a particle size to do this kind of calculation. So we first did this analysis for assuming a particle that was not aggregated, a primary form, and we also did that as a function of the aggregate size as we measured. Either way, the condition would suggest that at the pH 7 we should have had transport through the column because of the repulsive conditions. Why is this the case then? We believe it's due to straining. Now straining is basically the mechanism by which particles can get removed because they're too big to pass through the pores, or there can be some chemical mechanisms that make the pores appear smaller due to electrostatic repulsion. And so the accepted value in the literature is this value pointed out here, 0.002, that says if the ratio of the nanoparticles, or the ratio of the particle itself to the collector grain diameter is greater than 0.002, then straining is occurring. And in fact, the conditions where we saw particle retention, it is above that threshold value, which suggests we're getting this sort of physical straining occurring under these conditions. And also where we saw the elution through the column, the straining was clearly not important. We're below this threshold value. The only situation that leaves us without an explanation yet is this in between. We're at a pH 5 at the higher ionic strength condition tested, higher particle concentration tested. So why would that be the case? This is a condition that should be favorable. At pH 5, again, the nanoparticles are positively charged, the core is negatively charged. We expect lots of attachment. But we can explain this with looking at blocking as a mechanism occurring. Particles will attach to the positive sites. They will attach to the favorable sites, and at some point they fill them up. They run out of spots. And so when you increase the concentration of the particles you're putting through, they're basically going to fill those available sites immediately. And so these experiments, we conducted experiments at a wider range of concentrations, from 100 all the way to 800 milligrams per liter, and we were able to calculate the fractional surface coverage of particles, and we see that it fills up those sites much faster at the higher particle concentration. So what we believe is happening is that the particles are literally filling up those favorable sites, and then from there they can be eluted. There's nowhere else to bind. Now that last condition where we saw breakthrough, it wasn't straining. We weren't, it couldn't be explained by straining, and it couldn't be explained by electrostatic interactions nor favorable interactions. And what we believe is happening here is that we're getting aggregate breakup occurring because we're at our higher velocity condition. We did not see this occurring at the lower velocity, but when we ramp up the velocity, we increase the hydrodynamic force acting on the aggregates. What we see is larger aggregates entering the column and very consistently sized smaller aggregates coming through. And we've done a mass balance and really can show that looking at the distribution of aggregates, distribution of particle size being injected, it's not the same. It does not explain these smaller aggregates being eluted. So what we believe is happening is that the aggregates work their way through the column. They feel that hydrodynamic force causing them to break up and reform, or at least break into smaller sizes of particle aggregates that can work their way through the porous media. So you can think of it by this sort of cartoon, that at the lower flow rate under favorable conditions, they're going to deposit and eventually fill up the spots. But at a high flow rate, they'll deposit, but there'll be enough force to push them through the pore. Whereas in an unfavorable condition, as you can see off to the right, the particles will be in an aggregate form, but feel the repulsion from the collector grain, and it will effectively make the pore space even smaller, so making it more constricting and enhancing the amount of straining. All right, so that's the work I've done in the column. In the interest of time, I'm going to jump to the parallel plate. In this case, we wanted to corroborate what we had seen in the column in this visualization method. Here we labeled the particles with a FTSE label, and we used a glass surface. So the chemistry is very similar, pH 5 and 7. So the same sort of positively charged particles at pH 5, negatively charged at pH 7, a range of ionic strength, and a couple different flow rates. So the particles, as I mentioned, are positively charged under one condition, negatively charged, but we actually see a sensitivity of this to the ionic strength, and so when we increase ionic strength, there's a collapse of that electrostatic double layer, leading to the particles to be less stable. And that's very clearly seen when we look at the diameter of these aggregates increasing with ionic strength as well. And in fact, this blue line indicates the transition from nano to micron scale particles. So once again, using DLBO theory as a first approximation, we expected the particles to deposit extensively at pH 5 and to be repelled at pH 7. And the attraction would become more pronounced, especially at pH 7, as we increase the ionic strength, because we're overwhelming the double layer and overwhelming the repulsion, and over time we see a transition to a more favorable regime. So what are the results? Well, first we did the calculations for the mass transfer rate coefficients based upon the primary particle size. And we saw the trend as we might anticipate. At pH 7, where the particles were negatively charged, at first very repulsive, but as we increased ionic strength and they became less negatively charged, we saw greater deposition. So this is the transfer rate as a function of concentration. So we see the expected trend. It becomes more favorable for attachment. pH 5, the prediction would suggest that similarly, they become less charged, less positively charged, so less favorable for attraction. However, it's not that simple because our data really shows that they're aggregating. So if we use the values for aggregate size, we see an interesting different trend here, which is initially we see the same as before. We see that this is unchanged. pH 7 is unchanged. Where we see the interesting difference is at pH 5. Initially, we see it becoming less favorable because the particle interactions with quartz becomes less favorable, electrostatically favorable. But we get to sort of a transition point, and all of a sudden it becomes extraordinarily favorable. We have much more deposition and mass transfer to the surface. All right, so why is this the case? We wanted to identify what the other forces might be that are involved in the transport of the particles to the surface. So we did some calculations with the Smolkowski-Levitch approximation for this sort of idealized system where we can see entirely favorable, where any particle that would attach to the surface would stick. We wanted to compare this to our experimental condition. Now this is designed, this was to be a diffusion limited condition where there would be no other transport mechanisms involved. So that if what we found experimentally was greater than that of the ideal, it's suggesting there is some other external force engaged in the process. And that's indeed the case. So if you look at the right, you see roughly at these lower ionic strengths, there is one outlier here, but for the most part, we're seeing that our ratios are very close to each other. In fact, we're not too far off from the idealized system. But as we get to a higher ionic strength, we start seeing this notable increase in this ratio, which suggests there's an external force involved. And it may seem obvious, and yet, interestingly, somewhat debated in literature what that might be. And we put forward that it's contribution of the aggregation leading to greater amounts of settling and removal by gravitational forces. And so to confirm this, we decided to look at the particle deposition flux by sedimentation and look at that relative to the deposition flux by diffusion. And based upon sort of these being the two fluxes, we can basically relate the settling velocity from Stokes' law versus our idealized mass transfer rate coefficient. So if the settling velocity is greater than K ideal, it's basically telling us gravity is not only involved but dominating as this value gets higher. And so this shows us to be the case. As we get to these higher ionic strengths and the particles are aggregating dramatically, the contribution of gravity becomes quite substantial. Now, this can actually be quite handy if we want to think about ways to remove particles from a treatment point of view. If it's this sensitive to relatively small changes in ionic strength, to be able to get that kind of aggregation and destabilization, we can exploit that for a separation technology. All right, so skimming through these summary, I just wanted to go on finally to some work we've been doing with natural organic matter and bacteria. Because if you're dealing with wastewater or any natural waters, it's impossible to have a system without these present. And so we wanted to identify this contribution, especially in light of the fact that our working hypothesis was that bacteria would play a role very similar to colloids in facilitating the transport of a contaminant. There's a really robust body of literature on what's called colloid facilitated transport, where naturally occurring colloids could have a dissolved contaminant sorb on and therefore be a mechanism to help it move through the environment. And my thought was, well, bacteria are going to be ubiquitous, and if the nanomaterials have the ability to sorb and to attach to the bacteria can basically be its vehicle to get further than we might otherwise anticipate. So this is what motivated this work. And we conducted this in the column and the parallel plate. However, today I'm going to focus on the organic matter and parallel plate work, both in time and, frankly, the bacterial work has become very exciting and interesting, and I think not quite ripe enough to present to this group, but stay tuned. I think it's turning out to be quite an exciting area. We've been working with natural organic matter in the range that simulates that would occur in groundwater or surface water. Our experiments have been conducted at 1 milligram per liter. Organic matter is measured by total organic carbon. Now, for those of you who are less familiar, natural organic matter is basically ubiquitous in any water because it comes from the decomposition of plant material. And there's a wide range of sizes and types. It's the most heterogeneous material you can imagine. And it makes it a bit of a complex material to work with. So we chose a model organic matter, which was Swanee River humic acid. It makes for an excellent standard and model to use in experiments. And this has been found to basically have a net negative charge. So the experiments were conducted with the titanium nanoparticles, also fluorescently labeled, in the presence and absence of the organics, two pHs that I've discussed previously. And this time we added the complexity of working with both potassium and calcium at a single ionic strength and flow rate. All right, so you can imagine the sort of the two scenarios here where we conducted experiments up to now that you've seen here in the absence of NOM, where we conduct experiments here, and we're comparing it to what happens now in the presence of this organic matter, which you basically can think of as a very complex polyelectrolyte, very heterogeneous. So at pH 7, this is the data I'll focus on. Remind you, at the pH 7 we have negatively charged titanium. So here the electrophoretic mobility in potassium chloride, and in the presence of the calcium, we have the calcium basically having the capacity as a divalent salt to neutralize the particle more. The calcium has that capacity to collapse the double layer. So we see the particles are much less negatively charged in the presence of calcium. And similarly, because they're less negatively charged, they don't repel, they have the capacity to aggregate more. So in the presence of calcium, we have much larger aggregate sizes, as the plot shows on the right. Now, when we add the humic acid, or the natural organic matter, we see an interesting trend. And so in the red, for those who see it as red, here this is what happens when we introduce organic matter in the presence of calcium. So it becomes much more negatively charged, which is no surprise because the organic matter itself is negatively charged. And in the presence of calcium, it also becomes slightly more negatively charged, although not as much of a difference as you might imagine. The calcium also has an effect of being able to enhance the amount of binding of the organic matter onto the particles and similarly onto the glass surfaces. So it has an interesting effect on the stability of the particles. They render them more negative and in some cases then more stable, at least in the case of the potassium. And so we can see these effects in the effective diameter. When we add the organic matter, they're more stable and we see a decrease in particle size, and the same in calcium. What does that mean? So when we get these nanoparticles in a natural water, we've got organic matter present, they're actually going to be more stable than we might anticipate. All right, and how does this play into the transport? On the left, we're assuming a primary particle size, and on the right, the aggregate. And in either case, we see that the divalent salt renders the particles more adhesive. Basically, more is adhering to the quartz surface. And when we have added the organic matter, as we mentioned, it's more stable, we see a decrease in the deposition. Whether we're assuming primary particle size or an aggregate size, the organic matter has reduced the amount of attachment. So it's going to make these particles more mobile in the environment. But what's important to note here is with their primary particle size, the difference is twofold. But when you are considering the fact that we actually have notably sized aggregates, the difference of having organic matter in the deposition is substantial. We have much more of the particle mass staying mobile, and many times more than if it was just a primary particle. All right, and this is, and the humic acids effectively don't really affect the interactions as much as you might imagine. The presence of a humic acid might render the particle, as I mentioned, more negative, might increase repulsion, and we see that in our aggregation and our deposition results. But the question is, why are we seeing really any deposition at all? If they're more negatively charged, shouldn't they remain stable? And why are they? And they are remaining stable to some extent, but what's happening? Do we have the calcium causing some bridging effect? There's some issue of whether maybe there's some stabilization rendered by these polymers, which could be possible. And this is an area I think that's kind of exciting to look at. Now beginning to look at we're beginning to look at some additional organics and organic material to see how important this contribution really is. But the overall trend that I want to be the take-home message is that whether we have humic acids or not, whether we're at pH 5 or 7, I only showed the pH 7 data today, whether we're in calcium or potassium, so you can sort of take out a lot of these conditions, we see two critical trends, and I think this is the most important observation of note here, was we're considering our transfer rate to the surface, that it's a function of aggregate size and of the particle charge, the electrophoretic mobility. As we increase the aggregate size, we're going to have greater amounts of deposition by a range of different transport mechanisms, and we're also going to have increased transport to the surface, or excuse me, increased retention at a surface as we neutralize the surface charge. So you can see as we're neutralizing it, as it goes towards zero, we get more retention on the surface. And there's some really great messages here on how we can design removal and treatment technologies based upon these observations. Okay, and I think I've sort of made that point, so I'm just going to comment that I think this microscope-based technique is really very exciting. My group's the first to publish on the ability to visualize the nanoparticles in solution and look at their aggregation and deposition behavior. And I think that there's great promise for being able to apply this technique for a variety of different nanomaterials and in aquatic scenarios. Overall, the fate of the nano-titanium dioxide is going to be a function of the solution chemistry, the particle concentration, and organic matter. And as we're seeing now in this additional work, I'm working with some pathogenic E. coli. We see those E. coli love to bind our nanomaterials and enhance the transport dramatically. And the most important of these parameters is NOM presence, pH, and degree of aggregation. And yeah, I will leave it at that and go on to sort of a summary of what else I have going on in my lab, if you wouldn't mind the next few minutes to complete what other projects that I have. So the overall sort of way I describe my research group is in the adhesion and transport of environmental particles in water. My work was developed originally working with bacteria, and I've worked with a range of organisms, and in the last few years I've gotten to this nanomaterial work as well. And these are the systems that I do. I actually have developed recently a new flow cell that we're synthesizing right now, which will actually, we're etching porous media into silica wafers so that we can actually look at two-dimensional porous media under this system. I'm very excited about the potential for working with that system. But it's really a combination of indirect and direct visualization of particle movement in such systems. And there's sort of three areas of my work. The first is the direction I'm going as part of my NSF Career Award, which is looking at the fate and transport of materials in water treatment, specifically nanomaterials. So I'll be working with a wide range of nanomaterials that are commonly used in industry, both coated and uncoated. One of the challenges is the coating. So today I talked about uncoated nanomaterials, but in reality, most nanomaterials have been coated. Why? Because we want them to be dispersed. There's some sort of usually organic coating or polyelectrolyte on the surface, and those render them much more stable and make the removal much more challenging. So the question is, can our traditional techniques of coagulation and flocculation and filtration remove these particles? And are our existing infrastructure technologies sufficient? Sort of the meat and potatoes of what I've done but not presented today is looking at microbial fate and transport. I've worked with Salmonella and E. coli primarily, but also with Cryptosporidium and a few other bacterial strains. And I'm very interested in the features of the bacteria that render them mobile in the environment. One of the things that I've been doing in the last couple of years that's really exciting, I hope I didn't step on something to cause it to shut down, and I apologize for those of you watching on the computer. Very interested in how the environment affects a bacterial pathogen. So we found that we worry about a pathogen getting from point A to point B. And we spend a lot of time doing transport models and simulations and experiments. But we never ask ourselves, is the pathogen that left point A still a pathogen when it gets to point B? Has that exposure to the groundwater or the surface water, or whatever temperature fluctuation, seasonal fluctuation, has it rendered it now a non-problematic particle? And so in my group, we've been looking a lot at some molecular tools to identify expression of pathogenic sequences. We see upregulation, we see them becoming more virulent as a function of environmental exposure or less. It's very exciting because we see in certain conditions, we see organisms becoming not only more pathogenic, but more antibiotic resistant. And this has a huge amount of impact in the environmental health area where we worry about how we regulate bacterial transport. And additionally, I've done a lot of work looking at how microbial surface polymers, lipopolysaccharides, extracellular polymeric substances contribute to the cell survival, specifically both in transport and through disinfection processes. And finally, because I'm interested in why cells stick to surfaces in porous media, I've gotten into working with some material scientists identifying what are the properties of surfaces that make them anti-fouling. How can we design a antimicrobial surface? So I've worked with people in desalination who are making desalination membranes. I've worked with material scientists who make thin film coatings with zeolite, and also currently working with a fellow who makes these super hydrophobic surfaces to minimize cell adhesion. And in my microscopic system, I'm able to visualize it and really rigorously identify the anti-fouling behavior of the materials that my collaborators have generated. So it's an exciting new area. So with that, I just want to thank my students. I have currently, I've listed up there 4 of my PhD students whose work I've touched on today, and also 3 who've graduated. I'm very proud because the product, what we really produce is you guys. We're proud of them. Geshen is now a postdoc at the EPA, Bharat is a postdoc at Yale, and Nick is now a new faculty member at Chungbuk National University in Korea. So I'm very proud. And I think I'll also mention just here, I have wonderful collaborators through the UC Center I'm part of, and also through the USDA. So with that, I'm happy to take any questions. I did mention my funding. Thank you, funding, EPA and USDA.
Thank you, Sharon. So we have questions for Sharon?
Sharon,
Yes, I have.
here we are talking about aggregation,
Mm-hmm.
but also it is important to talk about de-aggregation.
Right.
Eventually, when we do groundwater, we don't want these to in your removal is fine. Water treatment, we can aggregate them and remove them. In groundwater, we don't want to transport
Right.
that should be just. So eventually, if I understand correctly, the center that you're working on, eventually they are trying to work on synthesizing nanoparticles that we have a better control on their transport. Is it true?
That's an ultimate goal, not necessarily the primary. That's not the primary task. The primary task is, from synthesis to transport to toxicology and trying to model across. What are those key parameters in nanomaterials across the board that might allow us some predictive tools for the health consequences? But the ultimate goal in all of this would be, how can we design a smart nanomaterial that has the functionality we want when it's in the product we want, but then when it gets into the water environment and it's done, can we have some sort of smart coating? I mean, I think that's what's an exciting idea. Is
That's what I really meant.
Yeah.
Just eventually. And then the other thing is that you have a lot of free radical reactions occurring on these surfaces eventually. And what would kind of effect would they have in the transfer of the particles eventually? Because the titanium dioxide is not going to stay titanium dioxide when it's moved in groundwater. It
Absolutely
changes
right.
through oxidation, reduction, and so forth. The transport will change in a larger distance. So what do you think? they're going to work
I've worked with some nano irons, hematite and magnemite, and looked at the different sort of stages of oxidation on these
Right.
different iron, and definitely that plays a substantial role. But you know, maybe I'm oversimplifying it, but I really believe it comes back down to the electrokinetic properties. You know, if it changes its oxidation state, it's effectively changing its net charge, and in that we see a different aggregation rate and stability and subsequent transport. So I don't think it necessarily matters exactly what the oxidation state is,
Yeah.
as much as how it changes the physical chemical properties of the nanomaterials.
Thanks.
More questions for Sean? Well, if not, let's thank Sean.
Thank you.